DOE CSGF Fellow Kelly Kuchansky in the field of Earth and Climate Science at the University of Colorado.
Welcome. My name is Kelly Kuchansky. I'm here to talk to you about snow. And I'm excited to be here at the CSGF Annual Program Review, where I can talk to some of my favorite people about something that I think is both beautiful and also important to us and to our climate.
Snow is one of the most widespread surfaces on Earth. It covers about 25% of the planet's land, plus millions of square kilometers around both poles. And wherever that snow lands, it dramatically alters the thermodynamics of the surface. The temperature of the Earth is shaped by a balance of energy between what comes in from the sun and what actually sticks around on the planet. How this balance plays out is controlled by what happens on the very surface of the Earth. And I have here 6 common surfaces: dirt, rock, ice, concrete, water, and snow. Out of all of these, the snow really stands out. Let's say it's a bright, sunny day. Most of these surfaces are going to absorb between about 50% and 90% of that incoming sunlight as heat. But the snow is only going to keep about 10. It's really reflective, and it sends most of that sunlight back off into space or the upper atmosphere. We see something similar with heat in the air. These are pretty solid, and they're going to transfer heat from the warm air into the ground below at rates between about 0.5 and 2 watts per meter per Kelvin. But the snow is not very solid at all, and it's only going to transfer that heat at about 1/10 the speed of solid ice. It's 90% air, kind of like a good down jacket, and that makes it an excellent insulator. Overall, snow is an excellent barrier between changes in the atmosphere and in the ground. It keeps cold things cold and hot things hot. The patch of my yard where I took this from, which is green grass now, is going to melt a lot faster than the areas around it that are still white with snow.
When I was growing up in England and New England, I thought of snow as this cold, soft, flat, fluffy thing, kind of like a cold, cold blanket. And it is like that in places. But in a lot of the world, it's not. In many places, the wind rushes over snow and carves it into shapes. Like this sastrugi you see here. It's a word from Russian, meaning anvil, directs the winds around it. Or like dunes, photographed here in Antarctica, here in temperate green Hungary, and here on the frozen methane-covered surface of Pluto. Bedforms like dunes alter the shape of the snow surface, but they also alter its thermodynamics. The wind moves mass from one place to another, and it creates roughness elements that can leave thin or bare patches on the surface, which heat fluxes through very effectively, reducing the insulating properties of the snow and allowing the underlying surface to warm faster. Despite their thermal properties, these bedforms are not yet well understood at all. We're talking about a field where, when I started my PhD in 2015, one of the most important sources of references was a series of notes taken by a British geographer with a beautiful mustache who traveled across British Columbia by train looking out the window in 1914. So we don't know much. But I want to talk to you about finding out more and about the growth of snow bedforms. I've studied these bedforms for the last 5 years, largely in the field. I've gone up to a place called Niwot Ridge, 12,500 feet up in the Colorado Front Range, and spent 3 winters or so there setting up time-lapse cameras and watching the way that bedforms evolved in the snow. And let me tell you, they are gorgeous. Here in this video, You can see snow being deposited in 2 dunes that move across the surface. And what I love about this, they're small, cute, just about 20 centimeters high, is that they're really responsive. You can see them shifting second by second as a gust or a pulse of snow comes through. In the second video, here, we look at the most common bed form on Earth, sastrugi, and watch them erode downwind. These bed forms cover almost all of Antarctica, as well as lots of sea ice. And as far as I can tell, this is the first time that anybody's ever figured out or watched how they move. At the end of my fieldwork, I had collected over 1,000 hours of time-lapse footage showing how these bed forms evolved, which increased the total number of observations by a couple of orders of magnitude. And that brings me in enough data that I can start to analyze it and figure out how these bed forms grow. And here, I'm going to show you the effect of wind speed, the major, though not the only variable controlling snow texture. And I want to show the probability that the surface will take different shapes as a function of that. So here, at the lowest wind speeds in yellow, snow, as you might expect, is flat. And this is what we see in sheltered areas in woods and houses. And it's flat up until the wind speed is about 9.6 miles an hour. After that, it forms these irregular, lumpy patches for a while, until the wind gets up to 27 miles an hour, after which we get well-formed waves and dunes. Now, this brought me to a point where I had this barely understood physical phenomenon, and I had just started to figure out what kind of processes drove its formation. So the next step, as a good computational science fellow, was to take these processes and build a numerical model of them to see what else I could discover about the bed form's behavior. So I started off by asking, can I simulate this? And the existing answer was no. I wanted a combination of model physics and resolution that didn't exist out there. So instead, I took a sand dune model, a community standard one called the Real Space Cellular Automaton Laboratory, and adapted it to make it model snowfall and snow cohesion and other processes like that. Along the way, I ran into a number of technical challenges that may entertain some of the fellows here. I calculated the uncertainty in the simulation from its measurements and dimensionalization, factors about 5 that had previously been ignored in publications. I optimized away a numerical bottleneck with the help of computer scientists from LL&L. I tried to parallelize the model and have made great progress in figuring out why it's hard. If anybody's interested, I would love to talk about why parallelizing a stochastic cellular automaton is a major challenge. And I pulled up a lot of old high school French to translate some broken and enigmatic documentation into more widely readable formats. So putting that all together, I get the first numerical model of snow bed forms, got it out there open source. And using this, I ran a series of simulations to show how snow surfaces evolve as a function of wind speed and the rate of snowfall. And these are also quite pretty. Here, you're looking top down at a heat map showing the heights of snow dunes. The wind is blowing from left to right, the same way the dunes are moving, and the colors are getting brighter as they get taller. We start with no snow, and then the snow falls and the dunes thicken and merge with each other and grow, until eventually we reach a quasi-steady state of relatively tall dunes migrating downwind. Can run these experiments for different snowfall rates, like you see here. Here on the bottom, we have a very low snowfall rate, which makes very widely separated, narrow dunes. And then at the top, a much higher snowfall rate. And you can see that the surface ends up being almost completely covered by much more closely packed waves. I ran a few dozen of these simulations. They're pretty fun. They take about a week each. It's still a slow model. And I pulled up a map of how wind and snowfall affect the surface geometry. So here you can see the wind speed along the bottom and the snowfall along the top. And then I'm going to show this first, the standard deviation of the surface. So you can see here that we've got when we've got the highest snowfall rates and lowest wind speeds in the dark purple corner, that corresponds to flat snow. And then the brighter colors correspond to snow with some bumps in it. So we get an 80% increase in standard deviation. What this means in practice, let's say we take an example. Ice that's 10 centimeters thick with another 10 centimeters of snow on top. Stick it in the Bering Strait off of Alaska because it's a nice convenient place to work. What this standard deviation would mean is that the thin spots in the snow are thin enough to increase the total heat flux going through the ice by up to 45%. That's pretty significant. We get a similar effect with snow cover. Here again, as a function of wind speed and snowfall, we see the cover fraction, which is the difference between the picture in the top left, 100%, where the entire surface is white and reflective, and the bottom right picture, Hungary again, which is mostly grass and not so reflective at all. This leads to about a half reduction in cover fraction, and because snow is so much more reflective than anything else, if we go back to that example of ice on the Bering Strait, this leads to about a doubling of the total amount of solar energy that gets absorbed, which in sea ice would correspond pretty neatly to a doubling of the melt rate in spring. So this brings me into the new science that I've uncovered. First, we've talked about the remarkable thermodynamic properties of snow and how the wind can sweep it up into bedforms. And we've also seen that the growth of these bedforms in high wind, low snowfall conditions can change thermal or sensible heat fluxes by 45% and can more than double the solar heat fluxes through a surface. Putting this together, places with high winds and low rates of snowfall will get faster warming for the same amount of snow. I'm going to thank you for listening in just a moment. But first, I want to have a quick word for the incoming CSGF fellows about grad school and surprises. Could talk a lot about these if we weren't virtual. I'm sure I would later in the evenings. But I want to start off by talking about applying for stuff, something the new fellows just did to be here. In particular, now that I've wrapped up grad school, I went back to everything I applied for, which is a lot. It's almost like a second job. And I tracked how much the award would have been worth if I got it and what the acceptance rate actually was where that data was available. And what I found wasn't what I expected. First, there are a handful of awards with nearly 100% acceptance rates. That's pretty good. If you can figure out what those are in your field, great, go after them. Second, the odds of getting an award really don't go down that much if you start looking at things that get more and more valuable. They go down a little, but not a lot. So if you're looking for new projects and writing proposals and coming up with ideas, go big. I'd like to thank a few of the many people who have inspired me throughout my PhD with my advisors at the University of Colorado and at my 3 practicums at Los Alamos and Lawrence Livermore. And finally, thank you all for listening. Any questions?